Atlas is engaged in developing an intercontinental ballistic missile capable of destroying targets at extreme ranges with a minimum probability of enemy interception. The weapon system consists essentially of surface-to-surface ballistic missiles, their handling and transportation equipment, their launching installations and equipment, their ground-based guidance elements, missile-borne guidance elements, and operations bases and associated installations, facilities, and equipment. The missile is launched vertically and guided during powered flight to coincide at a power cutoff point above the atmosphere with a ballistic trajectory from this point to the target. Guidance and propulsion end simultaneously at this point, some 5 minutes after launching, and the nose containing the warhead is separated to continue for another 25 minutes in a free fall along the gravitational ellipse. The entire guidance problem therefore consists in providing the missile with the correct heading and speed at power cutoff while still over friendly territory. A programmed autopilot stabilizes the missile and directs it onto the correct heading, and an integrating accelerometer cuts off the propulsion when the missile has attained the correct speed. If these inertial elements can be developed to the required precision, they will be self-sufficient. Or they can be built with components now available and radio-supervised by command-control signals from a precise microwave tracking and computing station on the ground. The Atlas military requirements were under continual review during the period of this report. Some of the requirements were relaxed to provide for a missile with a range of 5,500 nautical miles, a terminal speed near Mach 1, a circle of probable error of from 2 to 3 nautical miles, and an atomic or thermonuclear warhead weighing between 1,500 and 3,000 pounds. From July to October, development effort was accelerated on the components of a 1.5-stage missile, the XB-65, that could deliver a warhead weighing up to 3,000 pounds. A full-scale body section was built to verify the design, construction, and dynamic characteristics of the pure monocoque airframe, and to test some of the missile handling and transportation arrangements. The walls are thin stainless steel, varying between .016 and .040 gauge. The cylinder is divided by a bulkhead to form 2 integral tandem tanks for the fuel and oxidizer. The work is positioned in the fixture by fiberglass tooling rings, cemented to each skin section as it is added. When welding has been completed, the fuel and oxidizer tanks are pressurized to provide the necessary stiffening. The tooling rings are then removed, and the pure monocoque cylinder is supported only at the extreme ends. It is 75 feet long and 12 feet in diameter, and weighs only 5,700 pounds. When the external fittings have been attached, the pressurized tank is loaded onto the handling trailer, where it is also supported only at the ends. The specially designed pressurization trailer is attached to automatically maintain the correct tank pressures in transit. Here we see workmen walking freely on top of the pressurized tank while covering it for the trip to the test site. En route to the test site, the loaded trailer negotiates normal city streets and traffic without incident. The rear wheels of the trailer are power steered by dual steering wheels, enabling it to make an uninterrupted turn around this 150-degree downgrade bend in the narrow road approaching the test site on Point Loma. The test site occupies about 2 acres of military reservation on the seaward side of the point. It was completed in September, especially for the Atlas tank test program. Besides the 120-foot tower for vertical pressure, flow, and drop tests, it includes 2 metal storage sheds, a reinforced concrete control center, and a horizontal fixture for weight, balance, and vibration testing. After dummy nose and engine masses are attached for dynamic simulation, the test article is installed in the horizontal test fixture. Tests are then conducted for determination of the vibration modes and frequencies. Later, the test article is reloaded on the trailer for transfer to the vertical test fixture. By releasing the tension in the upper of these aft extension struts of the trailer, the entire tank structure can be stretched by its own weight in order to depressurize it for inspection and modification. The trailer is also designed to be used as part of the cantilever arm for erecting the missile on the launcher in the pressurized condition, as demonstrated here with a 10th scale model of a proposed Atlas flight test vehicle. This use of the trailer avoids the necessity of adding the weight of erection fittings to the missile. Built-in powered elevators on the missile trailer provide access to missile components and systems for pre-flight preparations. The trailer workstand is kept in place on the launcher until all such preparations have been made, when it is lowered back to the ground. The trailer is detached from the launcher arm and hauled clear for the launching operation. In the program review in July, a mock-up of this proposed flight test vehicle was authorized, and on 9 and 10 November, it was officially inspected by the Air Force Development Engineering Board. The proposed test vehicle was designed to provide data on single-engine propulsion system performance in flight, but incorporated a number of other basic design features of the operational missile. In this design configuration, the missile is 82 feet long and 12 feet in diameter. Its launching weight is 80,000 pounds, of which 66,200 pounds are propellants, JP4 gasoline, and liquid oxygen. The test nose serves mainly as a fairing for the missile body and is non-separable in flight. The body or tank section is of the same lightweight stainless steel construction as the Model 7-4 test article and is continuously pressure stressed in the same manner. Plumbing, wiring, and electronic equipment are all mounted externally in 2 equipment pods, one on each side of the body. As a reliability feature, both of the pods contain a telemetering and a command-destruct system, each complete with its own power supply and antenna. The aft section of one pod contains the electronics package for the fuel and oxidizer ratio control system. The opposite pod contains the primary power battery, a DC to AC inverter, the electronic and inertial elements of the autopilot system, and a radio microwave transponder. The transponder, which generates signals and relays data for radio microwave tracking, has been developed by refining an earlier Convair transponder for use in the first Atlas flight test vehicle. The autopilot system consists of a multiple gyro unit, a programmer, a servo amplifier package, an integral control unit, and an electro-hydraulic servo system. This single-axis laboratory model of the autopilot system is used to study its stability. The gyro unit senses deviations in missile attitude and originates corrective signals which are fed to the programmer. The electronic programmer reads flight instructions from time-keyed perforations pre-punched into a film loop. This experimental model has operated satisfactorily for over 2,000 cycles in the laboratory. Programmer output signals are fed into the servo amplifier, which boosts the electrical signals and directs them to the servo valves. These valves regulate the pressure and direction of flow to the hydraulic actuators. The main engine actuators position the engine thrust chamber in response to the pitch and yaw signals generated by the gyro unit. The heavy pendulum represents the actual engine mass in the test rig. Portions of this analog computer are used to introduce missile response and flight dynamics into the circuit to close the test loop. Translated to the missile, the system operation presents this appearance. The missile has no aerodynamic control surfaces. Although the propulsion section skirt is not jettisonable in the test vehicle, it is identical to the skirt used in the XB-65 to mount the booster engines and their accessories. In the operational missile, these are jettisoned with the skirts at the end of the booster propulsion stage, while the center engine continues to furnish sustaining propulsion. This is known as the 1 1/2 staging technique. Shortly before the required cutoff velocity is reached, the sustainer engine is cut off, and final precise velocity adjustment is provided by 2 vernier rockets. Verniers have a nominal thrust rating of about 2,000 pounds each at sea level. In the test vehicle, they are swiveled tangentially by the autopilot for roll control. In the operational missile, they are gimbaled for perpendicular movement as well, to provide precise attitude adjustment during the final or vernier stage of propulsion. The stop valves are pneumatically operated by solenoids to achieve instantaneous thrust decay at final power cutoff. The test vehicle main engine, of which this is a full-scale mock-up, is a liquid propellant pump-fed rocket now under development by North American Aviation as associate contractor. The turbopumps are driven by a gas turbine and generator using the main propellants. Pneumatic pressurization of tanks and engine control lines is furnished by helium flasks charged to 3,000 pounds per square inch. The propulsion system is capable of producing more thrust for about 3 minutes than 8 J-57 jet engines with afterburners at full power. Development testing of this rocket engine has been carried out at the Santa Susana test facility during the report period. In some of these tests, the engine produced its rated sea level thrust of 135,000 pounds for periods up to 63 seconds, the capacity of the existing propellant tanks. It is expected that both main and vernier rockets will meet schedules for captive firing tests of the first HACL flight test missiles at the new Missile Systems Development Stand to be built at Camp Elliott near San Diego. The Atlas military requirements were further adjusted in October, when information from the AEC indicated that the warhead weight need not exceed 1,500 pounds. In anticipation of this, an intensive design study was begun in September to determine the most suitable of several vehicle configurations for delivering the much lighter warhead. Upon review of these design studies by the Air Force in December, a decision was made to proceed with the development of a smaller 3-engine 1 1/2 stage missile to be designated the SM-65. It will have the same military characteristics as the XB-65, except for the lighter warhead. By adhering to the 1 1/2 staging technique, the basic design features we have examined will be retained. Thus, the development accomplished to date on the monocoque body structure the autopilot and propulsion systems, and the launching, handling, and ground support equipment is directly applicable to the new configuration. The SM-65 will be 75 feet long overall, 10 feet in diameter, and weigh 243,000 pounds at launching, of which 225,000 pounds will be JP4 gasoline and liquid oxygen. The nose, including the warhead, will weigh 3,500 pounds. Two booster, one sustainer, and two vernier rocket engines will furnish a total of 362,000 pounds of nominal thrust at sea level. 60,000 of this will be from the sustainer engine, and 300,000 from the two booster engines of an improved North American design. The gimbaled booster engines and verniers will be used for flight control during the booster stage, and the gimbaled sustainer engine and verniers during the final stages. All engines will be started on the ground, as in the XB-65. A full-scale mock-up of a two-engine test vehicle based on this configuration is being built for Development Board inspection in May 1955. This test vehicle, the XSM-65 Series A, will be unstaged and powered by two booster-type engines of an existing design installed in the non-jettisonable skirt. It will have a programmed autopilot for flight control and dual telemetering and destruct systems. Meanwhile, research and development in the general field of ballistic missile guidance has gone steadily forward. Convair has been developing a radio-supervised inertial system based on existing inertial elements and the company's extensive experience with microwave phase comparison tracking techniques. A 5,000 megacycle signal generated by the local transponder in the foreground was successfully tested with this antenna arrangement built on a single base line. One antenna is a conical scan type, and the others measure direction cosine. In the general field of aerodynamic heating research, applicable to the SM-65 nose reentry problem, several approaches are being explored simultaneously. Convair has been investigating both heat sink and transpiration cooling techniques in the 120-inch solar furnace and in the new 60-inch solar furnace. This resistance heating rig and this 20-kilowatt induction heater at Convair were used to produce surface temperatures in specimens of dense graphite up to 6,500 degrees Fahrenheit. The blast of this specially designed hydrogen-oxygen wind tunnel will subject heat armor specimens to stream velocities of 6,500 knots at temperatures of over 1,500 degrees Fahrenheit. This pilot model produces stream velocities up to 5,350 knots and specimen surface temperatures up to 4,500 degrees. Such temperatures and stream velocities approximate those on the separated nose of the Atlas missile after it re-enters the atmosphere from an altitude of about 500 miles at a speed of around 14,000 knots. This environment of the meteorite is a new frontier in the science of flight, and much remains to be learned of it. But progress on the project during the July to January period would indicate that nose cone heat protection will be added in time to the accomplishments we have seen in this period. Reduction of warhead weight, selection of a basic configuration, mock-up of an engine test vehicle, autopilot system development, electronics and instrumentation design, handling and transportation trailers, and monocoque body construction and testing. All advance the date when the United States Air Force will be able to destroy any target within 5,000 miles of bases within the United States in less time than it has taken to view this report.